not devoted to a specific topic. If you find it of interest, we can get together again and discuss specific topics of your interest one at a time. But before I get to the retrofit topic, I want to say a few words about what kept us busy during the last 10 years, new building construction and the military construction program. This is the biggest new construction program in the history of our country. We, the Army and the Corps of Engineers, started it by trying to adopt best practices and to learn from the private sector, but ended with the pioneering advanced requirements for new buildings, with no individual state having anything comparable as a state energy code for non-government buildings. This includes IPAC 2005 requirements, EISA-ready fossil fuel-based energy requirements, Core ECB 2010-14 for the site energy requirements, adoption of the ASHRAE Standard 189.1, and new requirements for building air tightness, which has recently been adopted also by ASHRAE. Now, when we came close to the end of this program, we as a Corps need to look at what will keep us busy for many years ahead. We have between 200,000 and 300,000 buildings in the Army, and will need to renovate many of them to meet new mission requirements, better working and living conditions, and new more stringent energy goals. There is no single source of information which can help us with this new task, and there are only few private sector companies which have been successful with the unique renovation projects which allow a significant energy use reduction with building renovation. So we need to develop a new set of skills to be competitive for the private sector in designing and managing renovation projects, and once again lead the way in this process. So let's get started. So today I will cover the following topics. I will talk about the energy requirements and goals for major renovation SRM projects. I'll show you some examples of building communities undergone or designed for deep energy retrofit. We'll talk about the core bundle of energy conservation measures to achieve deep energy retrofit. We'll address building envelope, HVAC systems, lighting systems, appliances, and then I will come to conclusions. So probably you already saw this slide a few times, so I just want to recap it. We have building site energy use reduction requirements, which are outlined in Energy Policy Act 2005. We have ECB 2010-14 for the site energy use reduction, which soon will be replaced by a different one, and I believe it will be referencing not ASHRAE Standard 90.1 2007, but it's a later version from 2010. We have a fossil fuel reduction requirement stated in EISA 2007. Army policy to achieve 8 net zero energy installations by 2020, 25 by 2031, and we also have an Army requirement to adopt ASHRAE Standard 189.1. So now, just to deconfuse you with all these requirements, I'll just show you which ones are more or less stringent. So actually here in this table, you have energy use intensity targets in kilobitu's per square foot per year. And as you can see on the site energy, the most stringent is the core energy ECB 2010-14, which is 40% better than the ASHRAE Standard 90.1 2007. Now, if a new standard will be adopted from 2010, probably it's much more stringent standard, which is 30% better than the same standard from 2004, and there will be approximately, as far as I know, about 12% energy use reduction against that standard. But so far, whatever will be the case, core ECB for new construction and renovation is the most stringent on the site. The next slide shows CBAC's examples for different climate zones for barracks, maintenance facilities, corps, brigades, and dining facilities. And if you want to get to the fossil fuel target, you can apply 45% of this number between 2010 and 2015, and 65% fossil fuel reduction starting 2015. So let's look at another table. This is kind of progress that we have for the ASHRAE Standard 100. It will be published sometime later this year, and it covers about 53 building types for all climate zones in North America, both US and Canada. And it addresses the site energy for typical buildings that are available in the United States, and it doesn't cover exactly all the buildings that we have in the Army. So we'll have to adopt our own buildings. Sorry?
We had I hate to interrupt you, we had a network issue, and I think we cut off about the last few slides. Would you mind backing up a few slides and going back over the information one more time? I apologize again.
It's okay. So I'm starting this slide. Okay, so
this one I think we'll on, yeah.
So I will go briefly over this last two slides. So this slide shows you the EISA requirements for based on the fossil fuels. So the table shows the CBEX numbers in kBTU per square foot a year, and then in order to get your target for 2010, you'll need to multiply it by 0.45, and starting at 2015, you'll need to multiply it by 0.35. So it will be only 35% left from this number. So the next slide shows the table with proposed ASHRAE Standard 100 energy targets for existing buildings. This standard later this year will replace existing energy efficiency standard for existing buildings that was issued in 2006, and it will cover about 53 types of buildings. However, Army buildings are not covered well in this table, so we'll have to adopt some categories as we see in the fit. For example, Army dining facilities will have a better representation by fast food restaurants here. And barracks will be like dormitories, and let's say maintenance facilities will be like other maintenance facilities. But in any rate, that will help us to meet our, at least get an understanding how to meet our goals with energy, and if we decide to adopt ASHRAE Standard 100 for the Army. This one is the most stringent requirement among all others. We started thinking that it will be easy to change the energy use reduction by 3% a year. So during the first few years, we were lucky to get below the curve and to get more energy reduction that is required by law. And we're talking about section 431 of the EISA 2007 requirement. However, during the last few years, we are not meeting this requirement. And the reason is very simple. If you take our requirement for 2015, it means that we need to reduce our energy consumption in the whole Army portfolio by 30%. So we don't have money to touch 30% of buildings, but if we have, it means that every single building needs to be renovated to net zero energy building, which is not feasible. So this is a very stringent requirement, and we need to find a way how to deal with it. So having said that, we need to state our definition of the deep energy retrofit so that we can spell out our requirements to our contractors with our new renovation project. So EISA 2007 and net zero energy installation energy goals cannot be achieved when new and major renovation projects are designed and executed based on minimum requirements, even including ASHRAE Std 189. These goals have a chance to be made with all funded projects designed and executed to achieve deep energy use reduction. So deep energy retrofit may have different definitions. In Europe, for example, the member states define it as nearly zero energy buildings, which for me doesn't make a lot of sense. It's not very specific. Some countries like Germany or Austria, they define it as a passive house level of buildings to which they need to be renovated. So given some experience with the deep energy retrofits both in the United States and abroad, my personal proposed definition for deep energy retrofit at Army is at least 50% site metered total energy use reduction and meeting proposed ASHRAE Std 100 EUIs, EISA 2007 already requirements for 2015, and at least 40% better than ASHRAE Std 90.1 2007. So these are a combination of requirements that are not competing but adding to each other. Because 50% site energy reduction depends upon what is the original state of the building. If it was built many years ago with no energy codes available, so it will be easy to get to 80%. If the building was built after 2004, it will be much more difficult, especially if the building is like a dining facility. So you can agree or disagree with the definition, but the definition needs to be made, agreed, and stated in all our requests for proposals. So let's look at what kind of examples we have from US and from overseas. We have a great database developed by New Building Institute, and it was the project funded by Energy Agency in Northwest. It has more than 50 buildings that were retrofitted using the deep energy retrofit concept. As you can see, some buildings were better 79% against the baseline, others were 69 or 46. So there are about 50 buildings in this database, and actually it's a great success story, and we'll be working with this organization to learn in more details what was the way to get to this energy savings. Example from our Army renovation project. In about 2008, INFOM wanted to renovate buildings at Fort Polk, not because of energy issues, but because of mold problem that we had. So having no energy deep retrofit in mind, we worked together with the Fort Worth district, and by the end of the day, we had a building that was about 50% more energy efficient compared to the other next to it similar buildings, both on electrical and thermal energy use reduction, and it had an air tightness of 0.1 CFM per square foot at 75 Pascal. It had great comfort, relative humidity below 50% all year long, and increased living area and no mold problems so far. So the same concept was adopted to another 30+ barracks at Fort Polk, and the same design is currently used at Fort Hood. Example from Germany. They looked at the area with about 200+ buildings for low-income families. So these buildings are pretty much similar to what we have with our barracks. And they were able to drop the energy consumption about tenfold compared to the baseline. Not only with the site energy, but also with the source energy. The way they did it was from fume energy conservation measures like insulation, windows, air tightness, heat recovery, and such. Plus, they connected these buildings to biomass-based central energy plant with a cogeneration. Another example is the former U.S. Army garrison in Bad Aibling. it's an interesting story where they wanted to demonstrate what's available technology-wise in Germany. So the private company bought it from the government, and in a matter of 4 years, they moved from the baseline to plus energy. They are generating more energy than they are consuming. And these are some pictures from some buildings were demolished, some buildings were renovated, some buildings were built in the passive house style. They put a huge PV field. They used some solar water heating on the roofs and a biomass central energy plant. Another example of deep renovation of a residential area in Frankfurt area, where they were able to go from 290 kilowatt hours per square meter a year to less than 20. Again, this is a private sector project, and there is definitely cost effective. There are no subsidies in this project. Another army garrison in Germany, Paul Revere village in Karlsruhe, where they did something similar with army barracks and other buildings to get low energy community. We did a paper exercise for Fort Irwin, looking at a cluster of buildings with four barracks, one dining facility, and a central energy plant. We did something same with all buildings, improved insulation, triple pane lower ear windows, greater building air tightness, high efficiency lighting, advanced control system, Energy Star appliances, and we tried different types of HVAC system for each barrack. In all cases, we're using the dedicated outdoor system, but with different ways of heating and cooling the building. So the bottom line is that with the additional $1.3 million for the cluster, the base renovation was priced about $29 million, so it was a plus up for $1.3 million. We were able to reach more than 50% of electrical and gas savings, and with a simple payback of 5.4 years, which is a reasonable project for ASHRAE. Now, if you go further and you look at the central energy plant and replace LPG with biomass, and interestingly enough, we have enough biomass in Mojave Desert. It used to be a Mojave forest. So instead of paying for removing this forest, they can use it for biomass for the boiler plant, in addition to the solar water heating. So with that concept, the overall energy saving will be net zero thermal and 50% electrical reduction, with the total payback about 10 years. Now let's look at what kind of books and materials are available to do something like that internationally. On the left-hand side, there is a great book that I picked up in France. It talks about different architects of buildings built in France between middle of the 19th century up to the middle of last century, and the ways how they renovate the building envelope with all the architectural details for each architect. It's about 300 pages, and it's available. If you look at the graphics, you don't need to speak or read French. It's readily available on the internet. On the right side, you see some materials from our project that we are working on with the DESA on the installation design guides for net zero energy installations. We developed masonry retrofit guidelines for already a couple of installations, West Point and Fort Bliss, and we are working with the other installations to develop something similar for them. Few other interesting handbooks and guides for building energy retrofits. the Handbook of Sustainable Refurbishment. It has interesting details on how you deal with both energy and sustainability in renovation projects, as well as a couple of guides which are already finished by TNNL, who worked on the project with the Building and Technology Office of DOE for K-12 schools and grocery stores. Another good source of information will be the Passive House standard for Retrofit. It has a book in English and German from German Passive House Institute, and there is a different document for passive houses renovation from Austria. It has interesting architectural details from both thermal barrier, air barrier, and such, and can be applied to different type of architectural buildings in the Army. So now let's go over energy conservation measures to be considered in deep retrofit. And I will start with the most important parts. It's improved building envelope insulation, walls, roof, attic, basement, ceiling, better windows, a reduction of thermal bridges, and cool roofs where they're applicable. Also insulated doors, vestibules to the high traffic entrances. Reduced air infiltration, efficient lighting, daylighting strategies, dedicated outdoor systems for ventilation, pressure and humidity control, low SRG HVAC systems such as radiant heating cooling, indirect air pre-cooling, ground coupled heat pumps and such. Important part is the reduced plug loads and using efficient appliances. And it needs to be considered based on the energy cost and also whether you want to become net zero energy and pay for renewable energy sources, or you have low energy prices. So we'll talk a little bit about that later. Reduced energy waste through combined heat and power. And so once deep energy reduction 57% are achieved, renewable power source becomes more affordable, for example, biomass or central solar water heating systems. So the key in cost effectiveness of the deep energy retrofit is using bundles of energy conservation measures. We are not talking about analyzing each energy conservation measure separately, because in this case you will never get to building envelope. Bundles have synergetic effect, and in this case, if you're paying more for the building envelope, you can reduce or eliminate the need of some mechanical systems. For example, in some climates, let's say climate 5 and up, you don't need air conditioning. And of course, this effective bundles depend upon climate, building application, and energy rates and such. So let's talk a little bit about each of these categories. This slide shows you building envelope functions, and one of the very important part is energy saving. So the heat exchange between the building and the outside occurs through conduction, radiation, and convection. And this is a kind of a schematic of the building envelope with the different approaches to its improvement. And you can see different elements that you need to pay attention to, which include roof, attic, windows, external walls, basement ceiling, basement walls, basement floors. Something that you can do with a renovation, something you can't do. So typical building insulation technologies used in the United States include spray cellulose insulation, spray foam insulation, and mineral wool or fiberglass bedding. If you want to go to more advanced technologies which are also available in this country, you can look at technologies with a high R value. And you can start with the vacuum insulation panels. Since a few years ago, these panels are available in the United States. You can look at super insulating light transmitting Calvol systems, which also available in the United States, and others down the road to mineral wool bedding over the R4. So here is a wide spectrum of different technologies and their thickness. For example, on picture number 4, you can see a foam insulation which has 300 millimeters in thickness, and it is available from stores like Menards or Lowe's, but not here in Europe. So, of course, the high insulation thickness, the lower thermal conductivity, and you really need to look also at the R value for different materials. Vacuum insulation systems are 10 times more expensive, but they are 10 times more efficient. So actually, if you are looking into the internal insulation of, let's say, historic buildings, you might want to consider vacuum installation so that you can save space for the mission rather than put heavy insulation on the inside of the building. In the guidelines that we are developing for net zero energy installations, you can find some components of the wall constructions for different types of classes of buildings with a description of how you put these layers and with a description of how much insulation you need to put and where to put your thermal barrier, air barrier, and vapor area in the whole package. This example of external wall insulation with the insulation level of R30, and here's on the right you see how the wall looks after the renovation. You can see some technologies used for external wall insulation. You can use adhesives or fastening, and actually the problem with the fastening is that here in the United States we have only 6-inch fastening for insulation, while in Europe you can easily find 12, 16-inch fastening, and the source of production both here and in Europe, they are manufactured in China. Another type of external installation would be the EPIs, and sometimes installations are not very interested in putting EPIs because they like brickwork, and in many cases plain vanilla type of facade doesn't look attractive. Today you can find brick type of EPIs in many applications, and here are some examples of brick type of EPIs installed by a Dryvit company. There's some examples. One interesting and cost-effective way of installation of existing buildings is prefabricated wall insulation. I just want to share with you a few slides from a European project which is a part of the International Energy Agency Annex 50 on the prefabricated installation for existing buildings. Here are some examples with the residential buildings. The concept consists of on-site installation and prefabricated model that are done in plants like we have with the manufactured homes. The quality of this products are much higher than when you have it installed on-site, and you can do a lot of things with that, incorporating your utilities in the installation. You can put pipes and ducts and different communications within those prefabricated model as well as windows. So these are some examples of installation process. We've seen the existing wall with some on-site frame that they're putting, getting the building ready for panels, and here come the panels. And the panels can have a different type of insulation materials, but that's how they are looking, how they're installed. And the overall effect is, again, energy conservation 10 times compared to the original baseline. And it has reduced cost because it's much cheaper to do it in the factory than on site. You can do it both with a facade and with the attic. So let me go back. So you can see already prefabricated attic that is installed in a matter of hours on top of the building undergoing renovation. Some details for a continuous thermal barrier for the wall to roof intersection. These are details again from the guide that we are producing together with Building Science Corporation. Some other ways to insulate attic and slabs. Actually, if you can't insulate building from outside, the way to reduce thermal breaching with the slabs is to put about a couple of feet of insulation on the slab, preferably from both sides, if not at least on one side. Thermal bridges for the balconies and slabs. Again, you cut a thermal bridge and you attach the balcony and to the building without penetrating through the insulation. Windows create significant thermal bridges. So when you install your windows, you want to install it not within the wall, but within a insulation layer, and you have a certain metal profiles to attach the window to the wall, and then you put your insulation around the window. It allows you to reduce thermal breaching by at least 50%. So I think that we don't need to spend a lot of time discussing air tightness. So we have ECB, the first one was issued in 2009. Another one May the 1st last year. We went through different versions of the air tightness protocol. The last one was developed together with a team from Air Barrier Association. The requirement for 0.25 CFM per square foot is 75 pascals. It's both for a new construction and renovation project. It's important not only to have the requirement of the protocol, but to make sure that every single project has a test based on this protocol to see if contractor is meeting this target. Statistics from about 315 data points for new construction and renovation shows that the average air tightness of the buildings is about 0.18 CFM per square foot at 75 pascals, and actually you spend less money and you have better building if you pay attention from the beginning, rather than you're trying to fix it going from 0.4 to 0.3 to 0.25. And in this case, you typically have the building that will lose its air tightness in a matter of a month because they're trying to seal the drywall instead of doing it right. But we have this requirement. There is a guide available on Whole Building Design Guide developed by our good friend who passed away, Tony Woods. He has a lot of good ideas on renovation of existing buildings, how to do that with architectural details and materials. It's available on Whole Building Design Guide under DoD, Corps of Engineers, and Energy documents. Modeling results show that if you make building more airtight, you can save up to 40% of energy, depending upon the climate, but it also will help us to deal with the mold issues. The payback, if you look at the data that we received from Tony Woods and things on the previous slide are between 2 and 7 years, which is pretty good, and it also gives us a kind of a warranty for our mold issues. These are graphs showing comparison between different types of buildings. As you can see, the set of bars to the left are for barracks. Among them, easier to achieve airtightness. The next one will be the third one from the right for office buildings. More difficult it is for maintenance facilities. And again, here's our great example with the renovation of Polk Barracks with a 0.1 CFM per square foot at 75 Pascal. Let's look at the HVAC systems. So why do we need HVAC systems? Those are to provide environmental control in conditioned spaces, to eliminate unhealthy space conditions and improve occupant comfort and productivity. And they are among major contributors to energy waste and inefficiency. And I would refer to ASHRAE Std 189, which is the most stringent for energy efficient requirements to HVAC systems. It's not an energy standard, but has the best requirements for HVAC. I would also refer to the residential grade heating and cooling equipment on Energy Star website. There are a variety of different examples of energy conservation measures. Within the Annex 46, we developed about 40 energy conservation measures fact sheets. We are currently finishing a book that has about 600 pages, and it talks about all this type of technologies and the economics and applicability for different types of buildings. So I would like to pay attention to a few things which sometimes overlooked, which are duct and pipe installation. It's not only energy, it's also mold prevention, and also level of seal of the ducts. Also contributes to significant energy use reduction. Well, we can talk about different types of systems, mechanical, natural, and hybrid. Important here is to use as much as you can dedicated outdoor system, because you have a different demand for ventilation, air, and thermal load throughout the year, and it's more cost effective to do it in two different systems than one. You have a smaller ducts, you have a smaller filters and fans. You don't use as much space for ducts. So this system gives you flexibility and energy use reduction. If you use a separate system for ventilation and humidity control and building pressurization, and another system complementing provides heating and cooling. So I just want to show you here the effect of different types of systems. So the first 1, 2, 3, 4 points deal with requirements for energy use reduction from insulation and lighting systems, and package and airtight. As you get into the package 4, you already have a variety of different systems that can be used for heating and cooling. And as you can see, it doesn't matter what kind of system you are using, they are almost all identical in the energy performance if you are significantly can reduce the energy load on the building. The only difference will be in the third point to the right, where you're using ground coupled heat pumps. Those are more efficient on the site energy, but require electricity for pumping, and therefore use more fossil fuel compared to other types of systems. So among important elements of the HVAC system, I would mention energy recovery ventilators. Those are must-to-use systems. They allow you to bring as much fresh air as you need at a minimum energy penalty, so they are transferring heat in the heating season and cold during the cooling season. Try to use the ones that have high efficiency. Today you can find heat recovery ventilators with efficiency up to 90%. Condenser heat recovery for supply air reheat. If you need to dehumidify supply air and you're using DX system, you are wasting heat rejected by a condenser. So instead of that, you're using condenser heat for reheat, so that you are not dumping cold air into the space and creating environment for mold. Another technology that you might want to consider will be indirect evaporative cooling. It's not a swamp cooler, it's a more advanced system that was tested at a few installations in the Army, like Fort Carson, Fort Bliss, Fort Irwin, and some others. If you use it in a little bit different configuration, you can use it in every single climate in the world, because what you are doing is you are doing evaporative cooling of the return air, and the return air parameters are probably the same all over the world. It's about 70 to 75 degrees temperature and about 50% relative humidity. So with that, you can either cool or pre-cool the supply air without using any kind of electricity. What kind of system to use as a complementing system? You can use either radiant or air systems. Air systems typically supply cold air, and again, if you have problems with humidity, that result in mold. It also requires filter change and fans to move the air. Another technology will be the radiant heating and cooling systems, which you can install either directly under the plaster into the ceiling. You can put them over the floor, or you can make them a part of the panels. So these are some examples of the radiant cooling systems, how they look with the panels, how they apply, you apply the plaster to cover radiant systems. We're working now on the demonstration project at Fort Detrick to show how it will work in the US environment, and there are multiple examples, including Chicago and Atlanta, where the system is already installed, and it's the first prototype. So how you install them in panels in the false ceiling, central system. This example of the radiant heating and cooling system at the Zhivov in Seattle. Those are net zero energy buildings built in Seattle. Radiant perimeter system at the core district in Seattle. So the next topic I would like to talk a little bit about is the lighting system. Advanced lighting is not only luminaries, it's also good design. And here you want to look at the design strategies. You need to try to meet your lighting requirements, not only LTDs or power density. You might want to look at the hybrid systems, which will be a combination of daylighting and electrical lighting. You want to look at the combination of ambient lighting and task lighting. And this, with the help of controls, you can reach much higher efficiencies that are currently required by ASHRAE Std 90.1 or 189. So these are some examples of using this advanced lighting design compared to the ASHRAE standard 90.1 2007. And again, we have developed a guide for lighting design both for new construction and renovation for 5 buildings. Let me go to that list. This is the list of buildings that we already have this type of guidelines with the design strategy and type of luminaries and controls. We are currently working on another set of buildings which will include educational facilities, warehouses, hangars, athletic facilities, health, and also security lighting for net zero energy installations, but the same guidelines will be available and applicable to all other projects. So this is an example of advanced lighting technologies. You have LED spot lighting. I believe it was the picture was taken in Seattle, and while the task light is definitely taken at the core building, at new core building in Seattle. And also you can find interesting to have different switches for receptacles for plug loads, so you can turn them off when you leave, so that you don't have the charger pulling a few watts an hour for unplugged equipment. Another important measure to reach your fossil fuel requirements is advanced appliances. So as soon as you are done with your building envelope and lighting systems, the most important part is your plug loads. And they're especially important because you need to multiply the energy used by 3.34 to get to the source energy, because the generation is very inefficient. You have no control in most cases about how power is generated, but you can reduce the need for this power, and therefore you might want to look at some advanced appliances. DOE database shows that only 7% based on 2011 data of government purchases they use Energy Star appliances. Though you might want to look at top tier list of appliances developed by EPA. There is another tier 1, 2, 3 from CEE. There are other groups, and we are currently working on the recommended list of appliances for the Army in collaboration with the different agencies for net zero energy installations, where you also need to look at comparison with the cost of renewable energy. Some examples of the future work. We are working currently on 3 different retrofit projects with the task force between DESA and FEM, looking at the deep renovation project at West Point. Here we have a potential for 60+% site energy reduction within Barracks renovation. Presidio of Monterey, we have potential with that project of about 72% energy reduction on the source energy and 60 on site energy, and again using the same list of technologies that we were talking about a few minutes ago. We are working with the Fort Carson on 6 similar buildings. Recently they renovated one of those, and they reached 24% energy reduction even without touching building envelope. They looked only primarily at HVAC systems and lighting systems. So can you imagine how much we can save if we cut those thermal bridges which you can see on the right, and insulate the building and put better windows? So we hope that we'll be able to achieve more than 50% energy reduction on this project. So now let's get to conclusions. So level of technically and economically achievable energy use reduction with major building retrofit depends on the following. Type of the building and its mission. It's much easier to achieve significant energy use reduction in barracks than in dining facilities or data centers. The climate zone the building is located in, San Francisco versus Fairbanks. Initial energy use by the building, codes that have been built to, or level of degradation since it was built or last time conditions. Important part is perseverance of the client to achieve energy goals. You need a teamwork to get there. Clarity of statement of these goals and minimum requirements in the RFP. You really need to replace the statement that you need to renovate to this legal requirement or that legal requirement. You need to put energy use intensity for site and source. You need to put certain requirements in types of windows and installation and many other things, and be a little bit more prescriptive, especially with the energy use intensity. You need to have a technical expertise of the project team. Your contractor needs to have some experience with the deep energy retrofit. You need to do economical evaluation of bundles ECM versus single ECMs, and not to single them out, because some of them they have a long payback like installation, or they have no payback. You need to bundle them and see what will happen then. You need to look at innovative business approach to energy retrofits. Energy use reduction can be easily achieved or easily achieved when you do the renovation without any energy in mind. You're already spending money, and it's a great sunk cost for your energy project. You need to have understanding and ability of procurement team to mitigate within the existing legal and fiscal laws and regulations. Important part is the quality assurance and quality control system in place. Even if you say that you want to have air barrier or you have continuous thermal barrier, you need to watch how it is designed and how it is installed. And one other important part is the market readiness to provide required products and services to achieve technical requirements. Every year we have, or every second year, we have solar decathlon in DC, and all 20 teams for already a few years that I attended this event, we're using German windows with the RM10 to 12, while we are struggling getting R5 in our projects. So a little bit about further core development with the deep energy retrofit. I already mentioned the DAS-FM task force to demonstrate deep energy retrofit with 55% energy use reduction with 3-arm installation. We're currently working on International Energy Agency ECBCS program NX61, development and demonstration of financial and technical concepts for deep energy retrofit of government public buildings and building clusters. And we have a number of countries involved, and actually we were lucky to get a lot of contributors from US. Our next meeting will be in DC this Thursday and Friday, where we'll see how we can bring all these resources together. So, and the German Energy Agency group are in charge of this project. And it will cover technology bundles for few typical building categories with specific recommendations on installation values, windows, and such. We'll do some modeling, and we'll develop some guidelines that will help to streamline the process. Actually, for some of these guidelines, we need some of your help. If we have somebody from centers of standardization dealing with a list of buildings that we were talking about lighting guidelines, we need some joints so we can develop these guidelines for specific standard types of facilities in those categories of buildings. The second subtask B will be developing all the business models geared towards national legal and fiscal frameworks, how you can legally combine SRM and ESPC funding. In subtask C, we'll demonstrate pilot deep retrofit projects, and then subtask D, we will combine all this information in the way that it can be easily accessed by engineers, experts, decision makers, and such. So we want to thank Corps of Engineers and DESA for support of our work dealing with the deep energy retrofit, because without their buy-in and support, we wouldn't be able to get even to this webinar. And with that, I would expect some of your questions, and if you want to call me or send me an email. You have my email address in the phone envelope.
Thank you so much for the presentation, Dr. Zhivov. We appreciate it. I have 3 questions right off the bat, and we only have a few more minutes on the line. And then I'll give an announcement about the AIA and GBCI credits that are available. Some of you have been asking about that. So from Captain Houston, he asks, what type of challenges have arisen when you're improving insulation on bases such as Fort Irwin?
Well, first we need to get a buy-in from the core district and contractor to get into this type of project. Actually, the level installation is pretty reasonable. It's not more than 4 inches, and you can easily use, if it's for installation at Fort Irwin, you can use available R5 windows, and we don't need to worry about air tightness. It's already known how to do that. So all technologies are available. We just need to have the level of funding that a little bit beyond what they typically use for this type of facilities.
Okay, and then...
So there are no challenges on putting in installation.
Sorry, I didn't mean to cut you off. Second question is from Ronald Chen in the Pacific Ocean Division. His question is, how is IMCOM's commitment to reducing plug loads? Specifically, like, what things are they looking at doing? Is it like turning off workstations at night, or using Energy Star appliances or modular furniture during design versus task lighting and overhead lighting? And how do those strategies come into play when working on energy bundles?
Well, we are preparing a white paper that will outline our desires, and then we need to have this discussion at the DESA level and with the Huntsville, so that we can agree how we will implement that if there is a desire for that. As an example of the bad practice, my personal computer that I have for Dell is pretty heavy, and it uses twice as much energy as another good Dell model, and it uses 4 times more energy than the top 10 US models. So actually, if we can look at the number of computers that Asset is buying for the core engineers, probably we can get a pretty good deal to buy a different model from Dell, unless we want to switch to a different manufacturer. So it requires discussion and negotiation.
Agreed, and I know that different bases are also looking at what can Garrison commands do and implement at their level, so there are choices being made there as well. And last question for right now is Tim Peasley asking, where are the lighting design guides available? And I would ask that we could probably make those available on the Facility and Energy website. So maybe I can work with you, Dr. Zhivov, to get those posted there. But for right now, where would you recommend they go?
Well, actually, I would be happy to send it to you, and you deal with that as you see appropriate.
Great. Well, that's all the questions that I have for this particular webinar content. And again, I really appreciate the in-depth analysis.
For the first 5 installations available.
And I have one last announcement. There were some questions that people had asked on how to get your AIA credits for your learning unit for your license. So essentially, we had a strong pushback from the audience stating that they really needed learning units for participating in attending the webinar event. unfortunately, we were not funded this year to provide a webinar program. We all felt that it was a really good initiative that we could put on, so we've kind of volunteered in this effort. So to kind of cut down on the volunteer labor that's required for it, we're bundling up 5 webinars at a time, which essentially means that we're going to provide 1 quiz for 5 webinar programs, and those will be consecutive webinar programs. You can either attend the webinar live or you can watch one of the videos. Following that, you will then take the quiz for all 5 and you will receive 5 learning units. So following this presentation, we will provide a quiz on the SNE website, and I don't think David or I have posted that quiz as of today, but you can look at that quiz at the end of the week, and I'll provide additional instructions on our webinar for next week. So if you have any other questions, you can feel free to email me, and I can kind of give you a rundown, and I'll try to post like an instructional sheet that will say how that's done. But that's for the past 5 webinars, and those will be for future webinars going forward. So thank you guys for your patience, and thank you, Dr. Zhivov, for the webinar today. We appreciate it.